I actually changed a few slides as I was listening this morning. I really enjoyed the talks this morning, and I thought, what is my perspective a little different than those talks? And here goes. So let me start with just saying that I'm a controls guy, really a dynamics and controls guy first, and I've started with TRI, as Marc said, to do things that are more complex tasks. So this is an example I actually showed last time Sergey and I gave back-to-back talks of a robot that can load the dishwasher. It's a complex, unstructured task, and the robot now is doing sort of all of the high-level and low-level planning to clean a cluttered sink and load it in the dishwasher. The mugs go in the top shelf, the plates go in the bottom shelf, the silver goes in the silverware drawer. And one of the cool things about working on this in industry is that we're actually trying to take this to a level of maturity that I think would not have been possible or the right thing for me to do at MIT. And we're now deploying these things at bigger scales, trying to understand what you do with rare failures that you detect, and how do you get serious robustness out of a system of this complexity. There's a lot of nuanced behaviors in here, like Wei Wei's talk this morning, which I thought was very impressive. There's lots of primitives in the middle here that are doing things like picking up the mug, sure, but also picking up silverware. Sometimes it has to nudge things out of the corner because it's a big kuka and a big hand and a little sink. It has to open the dishwasher door. It actually even has a little capacitive sensor on the hand so it can turn the dishwasher on when it's done. My favorite little primitive in the middle there is actually, it's a fairly nuanced task to pick up the plates very reliably. And I'm going to talk a little bit more about how we have to do that control and the implications maybe in the context of task and motion planning in a minute here. Okay, so there is task level robustness going on up there. So for instance, if C1 comes in as an adversary and closes the drawer when he was trying to put a mug down, you kind of feel like you're annoying the robot, but it'll eventually set down the mug, go pick up and open the drawer again. And we've tried to engineer sort of even robustness at the task level. These are the feedback loops that Jeanette was talking about. Monitor what you're supposed to think you think's happening, and replan if you need to. Okay, so I think we all agree TAMP is trying to address the whole ladder here from task level planning, discrete symbolic, to these more lower level continuous state time action ideas. And one of the things I want to think about here is how do you represent your motions at those lower levels, right? So I think one thing that we saw in maybe Sergey's talk and is a general theme I think here is that it may not be okay to think of the lowest level as just trajectories. And a big lesson for me transitioning from walking and flying things to manipulation is that tracking some trajectory, it's not about tracking the trajectory of the arm, it's about tracking trajectory of the objects in the sink in this case. And that's just too hard. It requires too much from your perception and control. So anything that you have baked in your TAMP framework that relies on the notion of a trajectory of the continuous variables, I feel like that's going to have trouble scaling, okay? So I think I want to talk about today about TAMP using feedback policies at the lower level, not trajectories. Okay, and I think relative to the previous talks, this is kind of a view from the bottom up. If I'm thinking of myself more as having spent more time on the dynamics and control, it actually, I saw a lot of examples of where the human has this discrete symbols that make sense in, how do we transition from this? We should pick something up, we should transition, we should do a finger gating, whatever. And then someone needs to write the controller to make that primitive happen. And I think largely people have been successful writing that way. I said it was a complex undertaking. There's a different view from the bottom up. And I thought I'd bring out, I actually threw this in minutes ago. So there's a little history here, but there's a view from the bottom up here, which is that the symbol grounding that we should be doing should be given to you from the controllers. It's not your right to just impose and say, we will find a controller for this. When the problems get more complicated, we should ask the controllers what they're capable of doing. And there's a natural description for that, which is in terms of a Lyapunov function or a value function. They're almost synonymous. One has an objective, one doesn't. One's just talking about stability. And we think about what the controller can do is take some set of states in this picture from a large set and try to drive it to a smaller set. Maybe that's the goal of control, and that's going downhill on a Lyapunov function. But what's also important here is that there's that inlet of the funnel is not everywhere. In fact, the controller can only guarantee that it's going to do well over a relatively smaller part of state space. So what you do, of course, is your higher level planning becomes composing these funnels into something that can work and solve the bigger problem. So what would it mean to take the TAMP problem and think of it from these feedback controllers, okay? So again, I threw these in last minute, I hope it's okay. So there's actually, there's a whole bunch of hard questions in the symbol grounding domain. Some of them, I think, actually in state space for controllers like pendulum and walking robots even, we have fairly satisfying answers in the sense that we have algorithms that will evaluate a controller locally and figure out with a natural objective function is to maximize the volume of the inlet of the funnel. You can try to figure out basically where this controller works in state space. And if you have a controller that's trying to swing up the pendulum, this is theta versus theta dot, the goal is here. There's a stabilizing controller at the top. There's a swing up controller here that has a particular region of attraction inside it. Then once you're in there, you've got your symbol somehow defined. And then there's a natural way to sort of use randomized motion planning to decide, do I need a new skill? Well, sure, if I sample someplace in state space and it wasn't covered by my existing skills, then I need a new skill. And there's even this sort of sense that you could be done in state space of like, I've got enough that if I sample, 10,000 times and I never found a place where I couldn't have a guarantee, then I'm done, right? So that's maybe the bottom-up view of symbol grounding for TAMP, and it actually got us fairly far. We had airplanes that could land on a perch and the like. This was more me making sure you guys are going to see videos on your screen. Okay, and you could do it for walking robots, and it even feels sort of fairly natural where you have one controller that's stabilizing a nominal limit cycle of periodic motion of the walking robot, and then if you have a disturbance, you turn on a different controller that gets you back, and those can all sort of come out of the natural strategy of just trying to cover your state space with controllers that are guaranteed to get me back. Okay, so now let's see how that works here. So this is not LQR trees, okay? This is an output feedback policy. It's actually a pretty subtle policy where it's going down, it's trying to reach until it feels some contact, it's trying to get its finger between the plates. Once it feels like it's detected that, it slides in until it's got other contact. There was some visual servoing with the wrist-mounted camera. And to get this right was actually very hard and had a lot of human engineering inside it, okay? And I don't think you get that from planning or MPC, right? So a lot of us think about, how do we make planning fast enough that we can plan trajectories online? And I used to think that was the best thing we could do. Like if I could take into account exactly what's happening right now, I can set myself up, I plan super fast, model predictive control, it's all good. I don't think you get here, you can't get here from there, I think. Because, not only is it partially observable, I think that's the easy thing, is that it's hard to know what your state is and you have to be robust to that. Maybe you can throw enough robustness and planning under uncertainty into your trajectory optimization or your motion planning. But I think even having the state, if you could get the state, that's not enough to describe the controller that Siwan wrote that was brilliant. He had in his mind every possible plate this thing's going to have to pick up. And he knows that there's some strategies that are inherently more robust. And the fact that it's triggered on sensors instead of as a function of state, this is inherently because it's not only a distribution over possible belief of possible states, but also a belief over the distribution of possible parameters like number of plates and mugs and lighting conditions and so you could do that, but I don't think you can do that on the fly, even in the land of big computation. Okay, so we've got a lot of work in my world of trying to make control through contact really robust. That the LQR story didn't work, partly just because contact you can't do linear control through nicely. In particular, when things get more complicated geometry than what we had in the walking robots with point feet were fairly easy, but complicated contact geometry broke a lot of those simple hybrid model approximations. And there's some stuff there that I won't talk about today. The other big difference here is that picture I had of how, what defines a state, how do we decide if we need a new controller, a new feature, these things, we need to extend that to think about output feedback motion planning. So now the notion of state may be in danger, it's threatened, it's maybe, not only do we not have it now, but we don't even know what it should be. So how do we scale this to output feedback? And this is more speculative, or actually I'm going to give more questions than answers here. Okay, but I tell you, a big part of this is having learned in the School of Hard Knocks how hard it is to do perception. We've made a lot of progress on it, trying to understand how to go away from the pose type representations that Chris was talking about. I think we're all sort of in the same camp on this, that you have to extend it to some more general descriptions. We've used key points in this work to try to show that you could manipulate key points and have that well-defined over a whole class of mugs. The other core perception technology that has been a good workhorse for us is this idea of dense correspondences. So we train deep networks to go from an image on the left is like we're putting a mouse over a part of the hat and saying, please find that point on the hat in the other pictures, and it's lighting up its belief over where that is. And the fact that it sort of tracks as well as it can in all these different views, it's just very stable and very good. It's been a workhorse for us to help bridge the gap between perception and control. So, but the problem is there is no spoon. So the notion of even what's the orientation of my plate is maybe the wrong question, right? So, and if you, and I'll try to make that point in a second here again, but if you really aren't allowed to use the word state anywhere in your TAMP, then how do you represent your motion? Maybe the policies is enough. How do you even specify the goal? I think these are the fundamental questions, and Sergey and I have talked about that plenty of times before. So, what's the state in this problem, right? So if you're thinking about, tracking the state with your Dart or whatever, and that's not a jab, but our stuff too, any of these, I think the state view of the world gets very uncomfortable when you're watching this video. Like, how many pieces of onion do I have to, oh my gosh, the state's changing, right? So, this shouldn't be just out of scope, because most of the tasks we want to do around the world are more like this than like a single object that has a sixed off state. Okay, we're getting some of our first tastes of robust output feedback policies for manipulation by putting, those dense descriptors and the like to work. Pete and Lucas have got a great series of work showing now, first with imitation learning, that they can close the feedback loop from perception and get pretty robust policies. But this was just with imitation learning, but it's just a taste of, I think, what robust feedback would look like in a narrow sense. And we're trying to bring our synthesis tools up to match that, so that we can, from a not CAD model necessarily, but from a physics-based understanding and control, we can design the same controllers. Perception has implications at the task level too. So watch closely in this video. We have perception systems that find mugs in the plate and in the sink and everything. But if you think carefully about what's happening here, you could sort of understand why the robot might have to put the mug and the plate down on the sink, on the countertop there, because it doesn't have enough dexterity in its hand to do the in-hand reorientation. So it sets it down in order to just get a new grab. Okay, but why does it put like the banana on the counter? See, that's the real question, right? Because we really want to be sure that we don't throw a mug away, okay? The fact is our perception system fails often in the sink. It gets much, much better on the counter, and the whole task is actually extremely robust now, fails very rarely, but it has to account for the individual perception failures, which happen often still. Okay, so I think the way that you come up with these controllers has to evolve, right? And I think DeepRL has opened my mind about it for sure. I think we need one controller that works for many different tasks, many different environments, and that's how you get these more robust strategies, like what C1 typed in for picking up a plate. Okay, so we are doing work on trying to model environments, distributions of environments, procedurally generating objects, and you name it. I do think that there's an essential role for data. I think there's only going to be sort of an empirical understanding of those distributions, I think. I would love to have like, it's just a Dirichlet plus a Gaussian plus whatever, but I'm willing to say it's a bunch of points and I have to generalize a little bit. But there's a lesson from robust control there, which I think a little bit of uncertainty modeling goes a long, long way. You don't have to get the distributions exactly right. If you just say, be robust, you could think of that as a regularization that works for lots of different types of exact models. All right, so I tried to pivot a little bit while I was watching this morning, but I tried to give you sort of my architecture for TAMP, which goes through feedback motion planning. And I think the recommendation, maybe the idea is start with what you can do with control and let the control dictate the symbol grounding, which then we have to think about a lot of other things in order to make that work well in a TAMP framework. I think it has to be output feedback. You got to embrace perception, partial observability. And I think the robustness comes not only from being robust to partial observability, but having one policy for many tasks and environments. And then, so where's the learning? I didn't use the word learning very often. I apologize to the organizers, but you know, we definitely have deep perception front ends. I definitely believe in empirical distributions over tasks and environments. I probably haven't gotten to the point where we needed to learn to plan at the task level. We're not trying to get the robot all the way to book a flight to Paris or whatever Leslie's favorite example is. But I think it's probably not a policy at that level. And, you know, but one thing that we're not doing is I'm not using learning to say that there's a gap between my simulator and my reality, and therefore I need learning. I actually think we can simulate things very well if we can get the diversity of simulations and design controllers by whatever means necessary. Give yourself gradients, give yourself symbolic. That's the problem we need to solve, and I think that will transfer fine, and we've seen lots of evidence for that. So, you know, just to sort of wrap up, we started thinking about this lately, and it's actually a super good TAMP problem, so for a low-level guy. You know, so there's obviously continuous dynamics going on here all over the place, but there's also some sort of logical state about, you know, is the knot there? Did I get a bow in there yet? Are the bows over each other, right? So where does that state come from? Where does that logical abstraction come from? I think that's a fun question. And then how do I, you know, how can you solve this TAMP problem with your tools? Okay, for those of you that were nice enough to try to open up my slides locally, you will be downloading right now a very small in-browser 3D animation of a KUKA moving around. And it's completely interactive if you want to play with it and zoom in or whatever. And I'm working like really hard to try to put my manipulation class online and have it be really a good experience for people this fall. So, and it'll be online enough that if anybody wants to participate or watch, there's a link at the top, and it'll be Googleable, I hope. But we're trying to get all of our manipulation stack to be basically something you can run in Colab, and no install, and you'll have all the 3D experience. Okay, I'll stop, and we get to do joint questions, I think, with Sergey.
Yeah, thanks, Russ.